Welcome to the Week 10 Math 2413 review. In this one, we'll be briefly going over the mean value theorem again, and we'll also be talking about how to interpret the derivatives as far as slope goes. We'll address some inflection points as well, and lastly touch on Logital's rule. Is that all the things you covered in the class this week?
Pretty much, yeah.
Perfect. All right, then let's go ahead and get started. So first off, if you'll recall the mean value theorem, which I'm going to abbreviate MVT, basically says that if we have a function that's continuous on a closed interval and differentiable on an open interval, then it has to hit its average slope somewhere within that interval. What we can write is, at some point, its derivative, which is its instantaneous slope, has to equal its average slope. And this is just our slope formula on the right-hand side. And again, our conditions are f of x is continuous on the closed interval from A to B, and differentiable on the open interval. Okay, so let's take a look at a couple of brief examples. First, I'm actually going to do a kind of non-example. So let's say we have the function f of x is equal to 2 plus the absolute value of 3x minus 3 on the interval from 0 to 2. Well, if we sketch that out, that's going to look very roughly like here we would have at 0, this is 5, at 1 we're going to have 2, and then we're going to have, at 2 we're going to have 5. And if I could draw better, this would look more symmetric, but this is roughly what this function looks like on our bounds. Well, you might be tempted to say, I know that f of 2 is equal to 5, and that's also what f of 0 is equal to. So my average slope should equal to 5 minus 5 over 2 minus 0, which is 0. And say, well, then there has to be a point such that my derivative is equal to 0. This is actually wrong in this case. The mean value theorem does not apply here, so there is actually no point where our average slope is equal to 0. The reason that the mean value theorem doesn't apply, again, we have to look back at our two conditions we have up here. First off, it is continuous, so it satisfies that condition. However, there is one point where it's not differentiable. And because it's not differentiable at this one point, the mean value theorem doesn't apply at all. In fact, we can just kind of intuitively see that here our slope is 3, and here our slope is negative 3, and there's no point where our slope is equal to 0. So the mean value theorem does not apply. Precisely because our function is not differentiable at this sharp term. That's the bottom of our absolute value. Make sense? Perfect. All right. Now let's go ahead and do a different example. This one that's a bit more like the problems I think you guys have been seeing on your homework. Let's say that you have a function and f of 2 is equal to 3, and you also know that negative 1 is smaller than f prime of x is smaller than 2 for all x values. Now the question is, find the minimum and maximum values of 5. Now, there's two ways to approach this. I kind of prefer the intuitive method, so I'm just going to explain that way. The idea behind the intuitive method is if we're finding the maximum value, then it should take the maximum slope every time, because that's going to lead to the greatest increase. Or in other words, the maximum slope possible is always going to be 2, which means we can essentially create just a linear function starting at the point 2, 3 with a slope of 2 going over exactly from 2 to 5 is 3. And that's fairly easy to calculate. We simply, because we go over 3 at a rate of up 2, we can see that this point here, the y value should be what we started at, 3, plus our slope times how far over we went, and that should give us 3 plus 6 is 9, for a maximum value of f of 5 equals to 9. Similarly, if we were interested in finding the minimum possible value, well, we would take the minimum slope all the time. So that would be a slope of -1. And again, we're going over 3. So for our minimum, we would do our starting value, 3, plus our slope, -1, times how far over we went, and that gives us 0. Now we can actually verify this is true by using the mean value theorem. So the way we'll do this is through what's called a proof by contradiction. We'll start out by saying, let's say that this is not our minimum value. Then we must have a point that's lower than it. So, by the mean value theorem, there should be a point so that something smaller than 0 minus 3 divided by 5 minus 2. This is just my average slope formula. I'm taking my second point minus my first point. This must be equal to, or I guess when we take this something smaller than 0 subtracts 3, well, on the bottom we have something smaller than 0 subtract 3 over 3, and this would have to be smaller than -1, because I would have something smaller than -3 divided by 3 would give me something smaller than -1. The problem with this, though, is now we have that at some point our slope is smaller than -1, but we're told that our slope is always larger than or equal to -1. So this is a contradiction. And what this tells us is that our assumption that we had a smaller minimum than 0 would be wrong. So 0 would be our minimum. Does that make sense? Good? Perfect. We could do the same kind of process with the maximum as well. Basically, that's how we can find our minimum and maximum values. To me, the intuitive way of just thinking, well, I'm just going to take the maximum slope every time, it makes the most sense to me. But if you have a different method that you prefer to use, let's go ahead and use that. So we'll do one quick practice problem with this, and then we'll move on. And I'll give you a minute or two to work on that. All right. That's all I got. You're good. All right, let's go ahead and go over this problem. Okay, so this problem is basically the same one as the last one, just with slightly different numbers. Again, to find our maximum value, we're just going to take the maximum slope. So we start out at 7, and then we move over from 4 to 6. That's a difference of 2, times our maximum slope is 5, gives us 17. And for our minimum, we're still starting at a y value of 7, still going over 2. This time our minimum slope is 2, and that would give us 11. Does that make sense?
Well, you should be kind of like turn it off.
I will address that.
Give me one moment, y'all. Whatever.
I mean, feel free to click the button as many times as you want. So, all right. Let's talk about some derivatives. Why do I multiply by 2? Okay, solid question. The reason I'm multiplying by 2 is because I am moving over by 2. So if we wanted to sketch out our picture, here's our x value of 4. Here's the y value of 7 with it. Well, at f of 6, I'm moving over 2. And my minimum slope, which corresponds to my minimum value, I'd be going up 2. So to account for the total distance upwards that I went, I would take my slope of 2 and multiply it by my horizontal distance of 2 to find my minimum. So I would have my slope of 2 multiplied by my horizontal distance of 2 plus the y value that I started at. And similarly for my maximum value. Except in this case, I have a 5 as my slope. And I'm still going over 2, and I still start at 7. Does that answer your question? How did I calculate the slope as 2? So I am working off the idea that if I have, that at my minimum, to get to my minimum, I would have had to follow my minimum slope the entire time. So I just picked out my minimum slope and said, when I reach that minimum, I must have followed the minimum slope the entire time. So it would have been a linear slope of just 2. Does that make sense? Yeah, it's just, I don't know how it's actually taught in your lectures. This is the way that I've always done it, just because it seems intuitive to me. So this is just kind of the way that I like to think about it. All right, so let's move on and talk about some. You learned how to do it with the formula? There's a whole formula. Dang. News to me, actually. Cool. Let's see. That's really all I have for the mean value theorem today, though. We touched on it last week a lot, so I'm not going to spend a ton of time on it this week. Next topic I wanted to talk about was derivatives and graph shape. So if you'll recall, the whole idea of a derivative is that it represents slope. Now this is a really, really good concept to understand because it makes a lot of things much easier. So for example, if we took a graph of x squared, just a quadratic, and we wanted to graph the derivative, well, we could look at it from here and say, wow, right here our slope is pretty negative. So we're going to plot a negative point here. We have a horizontal tangent at 0, which means that our slope is 0 right there. Right here, we have, again, a positive slope, which means we should have a positive derivative. And that would give us this nice linear shape right here. In other words, the graph of our derivative kind of tells us what our original function should look like, and also vice versa. If we have our original function, we should be able to look at the slope and graph the slope. So if we picked a point here, we could say, well, how steep is the slope? It's negative, so we're going to be at that same x value, somewhere negative. It's less steep than a point here, so it should be higher up than this point, but more steep than right here, so lower than this point. So if it belongs between these 2 points, we can see it might go there. Let's see. All right. So we'll do one quick example and then a couple of practice problems. A more complicated example of sketching the slope, that is. Let's say we have a function and it looks something like this. Well, if we wanted to sketch the derivative, a few things that I always like to start out by doing are identifying where the derivative should be 0. And the derivative is 0 when our slope of our tangent line is 0. So that's right here, and right here. So I'm just going to start by plotting those straight on my graph. Right there, there, and there. Now I also want to know where my function or where my derivative should be positive and where it should be negative. So here on this interval, I have a negative tangent line, so my derivative should be down here, or negative. Similarly, I have a negative derivative or negative slope from here onwards, so right along this way. Everywhere else it's positive. And I can see that on this portion, it's positive, and then it switches to negative. So I should have something that starts up here, decreases down until it hits negative. Then on this interval, it should be back to positive. And then moving onwards, it should be negative from here on out. And you can see we get kind of this nice cubic shape, which, if you think about it, the derivative of a quadratic of degree 4, which is what we have here, should be a 3rd degree. Does that make sense? Perfect. All right. Some practice sketches. Do they? I do not know how they're going to grade the exams. In this case, I just kind of put the arrows on by habit just to show that the graph extends continuously in both directions, but I don't know how they're going to grade the exams, so I can't really answer that one for you. I don't think they'd really care too much, but that's just my opinion.
Oh, yeah, that was the last one.
What are your thoughts? All right, Is everyone ready to go over these? All right. Okay, so let's go ahead. Starting with this first one. So again, I'm going to take the same process. I'm going to mark out all the points where I have 0 slope. And I'm going to put those on my graph. Now, up until my first point where I have 0 slope, I am increasing. So I have positive slope, so I should be approaching from the positive direction. When I hit that first 0, afterwards I'm decreasing, so I should be negative. And then I go back to being positive after my second 0 slope point. So that is what my first derivative would look like. Well, my second derivative is just the derivative of the derivative. So I can sketch that out as well. Again, I'm going to mark out all the points where I have 0 slope. In that case, it's just this first one. And up until that point, I have negative slope. Say like that. So I would start out negative, and after that point, I have positive slope. And that is just a linear function like that. For this last one, there are no points where I have 0 slope. In fact, I just have a constant positive slope, so it would look something like this. Okay. So that's this first one, and I will actually come back and address what this third derivative means, or what the second derivative means a bit. But we'll go over this last one just for completeness sake. So we are asked to sketch the original function if we start out with the derivative. So instead of going from here to here, we're kind of going the other way around and going from here back to here. So what I like to start out by doing is identifying my points where I have 0 slope. My points where I have 0 slope are going to be where my derivative is equal to 0. So that would be here, here, and here. So I'm actually just going to plot those really anywhere on my function here. So I'm actually going to put them here, here, and here. As long as I get the x values right, the y values don't really matter a ton. Well, I know that I should start out with a negative slope because my derivative is smaller than 0. And that means I should have a negative slope. So I start out with a negative slope. And here, I actually hit a point where I have, here I actually hit a point where I have 0 slope. So I go down and hit a tangent point. After this point, I should be increasing. And this is where I kind of need to, adjust where I put my y values for my horizontal tangents because I need to increase up until this point. After this point, I then need to decrease again. And then finally start increasing after this final horizontal tangent point. Does that make sense to everyone? Do all derivatives eventually become horizontal lines? The fourth derivative, that's a good question. If we took the fourth derivative, well, here we have 0 slope. So our fourth derivative would be 0. To answer your question, do all derivatives eventually become horizontal lines? The answer is no, they do not. We can think of a couple of easy counterexamples. For example, let's say we started out with a function that was a trig function, so just sine x. Well then, if we sketch the derivative of this, we're going to have 0 points here, 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 and so on. Or in other words, our derivative should equal 0 here, 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 here. And we start out with an increasing slope, switch to decreasing, switch to increasing, switch to decreasing, and so on. And you can see we get basically the same function, just shifted over. So in this case, our derivative would just kind of keep shifting over a bit, and it would never flatten out. So this is kind of some intuition behind why, if you just take the derivative of sine x over and over again, you'll never get to 0. The same thing happens when we have a function like e to the x. Its derivative is never going to go to 0, because when we take its derivative, well, we just get e to the x again. All right. Does that answer your question? Yeah, it's pretty neat. With polynomials, your derivative should always go to 0 after some point. So to clarify, polynomials, I mean x to some power with some coefficient plus something. And specifically, this power n has to be bigger than or equal to, I guess technically 0, and it has to be an integer. So if your function takes this form, then your derivative will eventually go to 0. Okay, but does everyone understand how I sketched my original function using my derivative? Okay, cool. In that case, I do want to talk about what this second derivative means. So the second derivative describes concavity, and you guys have probably talked about that in the course. So your first derivative is slope, your second derivative is concavity, and concavity is basically, does my function open upwards or does it open downwards? I like to think of it as, well, is it shaped like a bowl or is it shaped more like a hill? So if it's shaped like a bowl, we call this concave up. And if it's shaped more like a hill, we call it concave down. So specifically, when our second derivative is positive, our original function is concave up. And when our second derivative is negative, our original function is concave down. So for example, looking at this example we did earlier, or the practice problem we did, our second derivative is negative for all x values smaller than 0. So on our original function, for every x value smaller than 0, you can see that our function takes a kind of downward facing shape. And when our x value is larger than 0, our second derivative was positive. So for every x value larger than 0, our function takes an upward opening shape. And that's kind of how your second derivative is going to impact the way your graph looks. Specifically, we actually do have a special name for points where your graph changes concavity. So you can see at this point right here in the middle, our graph changes from being concave down to concave up. And what we call that is we call this an inflection point. And one thing to notice is this inflection point happens to occur where your second derivative is equal to 0. So again, an inflection point is any point specifically where our second derivative changes sign. So again, up here, our second derivative switched from negative to positive, so we had an inflection point. This is kind of analogous to your critical points. Your critical points are points where your function will have a maximum or a minimum. Your inflection points are points where your function changes concavity. All right, so one thing to note is that all possible inflection points have the property that the second derivative is equal to 0 at that point. Okay. All right. And we'll do a brief example of the inflection points in a bit. There is also the second derivative test, which also uses the second derivative. In this case, the second derivative test is used to classify maximums and minimums. So right here and right here we have a maximum and a minimum respectively. At each of these, we have that our derivative is equal to 0 because our slope is equal to 0. Well, if we wanted to figure out which one is a maximum and which one is a minimum, we can use the second derivative test to figure that out. Essentially, you'll notice at our maximum, we are concave down. At our minimum, we're concave up. This is actually always the case. So our second derivative test says if we have a critical point and we have that our second derivative at that point is smaller than 0, in other words, we're concave down, then we have a maximum. If our second derivative is larger than 0, or we're concave up, then we have a minimum. So the second derivative test can be used to classify our critical points into maximums or minimums. If our second derivative at that point is exactly equal to 0, well, it's inconclusive. You would need a different method to figure it out. All right. Perfect. Let's go ahead and do an example problem. Let's say we have a function f of x equals to x cubed minus x squared plus x minus 1. And we wanted to find the inflection points. Well, our inflection points all occur where the second derivative is equal to 0. So to find that, we'll need to find our first derivative, and then take the derivative of that, and then set it equal to 0. So then I get that x is equal to 1/3 as a possible inflection point. To check that it's an inflection point, I would need to make sure that my sign of my second derivative changes. So if I just make a brief little number line, I can see that when I plug in x value smaller than 1/3, I would get something smaller than 2. Subtract 2 gives me a negative number. And when I plug in x values larger than 1/3, I would end up with a positive number out. Okay, so here I have concave down, here I have concave up. Because my concavity changes, x equals to 1/3 is an inflection point. Again, I guess one thing to note is you should probably find the y value associated with it and write out specifically 1/3 and then whatever that y value is as your inflection point. But I don't think that's particularly necessary in this example. But that's essentially how we find the inflection points. Find the second derivative, find the points where the second derivative is equal to 0, and then double check that those points where the second derivative is equal to 0 actually have concavity changes. It was never really explained why there is a need for 2 derivative tests. Could I elaborate on this? Yes. It's really just personal. It's really just personal preference. you don't technically need two derivative tests. I'm guessing what you probably have been doing in the past is just making a number line for your first derivative and seeing where it changes sign. One reason that they might have come up with a second derivative test is because sometimes you want something a little more formal and rigorous than that. For example, when you're performing more proof style calculus, you don't necessarily want to say, well, I drew out a number line and it looked like this one was a maximum, so I decided it was a maximum. You maybe want a way that's a bit more rigorous than that. So that's where the second derivative test can be useful. But also just drawing a number line works for most situations. So it's really up to you whether or not you want to use the second derivative test or a number line instead, but it is good to know. What if the second derivative has a denominator that gets canceled out when equal to 0? Does it have a restriction at the x that would make the denominator equal to 0? Interesting. I'm not quite sure that I'm understanding your question. So right now, my interpretation of it is you're saying, what if my second derivative is like something like, I don't know, or at 0 specifically, you're saying, what if we get something that gets us like 0 over 0 that cancels? Is that kind of what you're asking? What happens in this case? Like if the equation had a denominator, for example, x minus 2. Oh, okay, so you're asking, like, what if we have a critical point with a horizontal? Okay. So remember, we have two types of discontinuities, mainly. We have holes and we have asymptotes. So holes are removable discontinuities. I think that's what you're talking about. And the primary issue here is that our function isn't differentiable wherever it's not continuous. So if it's not continuous, then it's not differentiable. So we can't actually apply the second derivative test at these points where it's not continuous. Or if you can, I'm not sure of how you would go about doing it. But I can't see a way that the second derivative test would apply when you can't take the derivative at that point. Does that answer your question? All right. Let's see. We'll do, I think, one or two good practice problems. And then we'll talk about L'Hopital's. And you guys will all like L'Hopital's because it makes all the limits a lot easier. And one notice reason. Okay. All right, let's go ahead and go over this. So first off, we're going to need to find our critical points in order to apply the second derivative test. So to find our critical points, we'll set our first derivative equal to 0. And first off, we need to factor this. One thing I'm going to do is I'm actually going to factor out an x squared for my first two terms, and a negative 4 for my second. Now from here, I'm actually going to factor out all of x minus 1. And that leaves me with x minus 1 times x squared minus 4, which is x minus 1 times x minus 2 times x plus 2. And that was all just factoring into a nice easy way, so I can see that x should be equal to negative 2, 1, or 2. Well, in order to apply my second derivative test, I'm going to need to take my second derivative. That's going to give me 3x squared minus 2x minus 4. Well, at x is equal to negative 2, I get that my second derivative would be 3 times 4 minus 2 times negative 2 minus 4, which gets me 12 plus 4 is 16 minus 4 is 12. So then I would have, because it's positive, it's concave up, which means I have a minimum. At x equals to positive 1, I'm going to have 3 minus 2 minus 4, which would get me negative 3. So then I have a minimum. A maximum. Yeah. A maximum because, again, our function is concave down. Lastly, at x is equal to positive 2, I have 3 times 4 minus 2 times 2 minus 4, which would get me 12 minus 4 is 8 minus 4 is 4, which is positive, so I'm concave up. Again, I have a minimum. Okay, so I've now classified my critical points using the second derivative test. I found that I had a minimum at negative 2 and positive 2 and a maximum at positive 1. Next, I need to find my points where my function is concave up or down. And to do that, I use my second derivative. So here I have my second derivative. I need to identify where this is equal to 0 in order to find where my possible inflection points are. In order to solve this, I'm going to be using the quadratic formula, just because I don't think it factors nicely. So the quadratic formula, I would have negative 2 goes positive 2 plus or minus the square root of negative 2 squared is 4, minus 4 times 3 times negative 4, all over 2 times my a value, so 2 times 3. And simplifying this, I would get 2 plus or minus the square root of, here I have 4 plus 16 times 3, so 4 plus 48 is 52, all over 6. And unfortunately, 52 is 2 times 26, so I could simplify that into 2 plus or minus 2 square root of 13 over 6, or 1 plus or minus the square root of 13 over 3. Now these aren't the nicest of numbers, but we can kind of use a general idea of what our quadratic should look like in order to prevent us from having to do too many difficult things. Here we have a positive coefficient for our largest power, which means as we approach positive infinity, we should have a positive number. So here, because I know that for any number that approaches infinity, we're going to have a positive value. Because our first coefficient is positive, I'm going to put a positive there. Next, I know because the square root of 13 is bigger than 1, I know that 0 has to fall between these. So I'm going to plug in 0, and I see easy, I get negative 4 out. Again, similarly, I can use similar reasoning to how I found this positive right here. find something as it approaches negative infinity. Here I would have a negative times a negative, which would give me a positive, times a positive coefficient gives us a positive. So whenever it's positive, we are concave up. Whenever it's negative, we're concave down. So we can say that our function is concave up on the interval from negative infinity to 1 minus the square root of 13 over 3, union 1 plus the square root of 13 over 3 to infinity, and it is concave down on the interval from 1 minus the square root of 13 over 3 to 1 plus the square root of 13 over 3. Did that make sense?
So the inflection points are 1 plus or minus 13.
Right. So these specifically would be our inflection points, because they are where our second derivative changes sign. So that means we have a change in concavity.
So pretty much the second derivative test, so I find concavity is pretty much the same thing as the first derivative, like increasing, decreasing, just find
Right.
Okay.
Yes. We're going to go ahead and repeat that for the online people in case they didn't hear. Your second derivative test for finding where your function is concave up or concave down is basically the same as your first derivative test for finding where your function is increasing versus where it's decreasing. Except in this case, you're just finding something slightly different. When asked to find the extrema, should we just use the second derivative test or manually plug in numbers around critical points? The second derivative test is probably easier. You can also use a number line. A number line isn't very hard either. Manually plugging in numbers around the critical points, I don't know how well that would work out because you might guess a number that's a little too far away. If you're using it to make a number line, then it's probably fine. But the second derivative test is probably pretty easy. Like we used it here. And the nice thing about the second derivative test is that it tells you for sure whether it's a maximum or a minimum, and you don't have to worry about getting a number close enough. Okay. Now I just have to wait for OneNote to finish pitching, and then we can move on. Perfect. Here we go. So now we have L'Hopital's rule. And this is a method for finding limits. So let's say we have a limit, and that limit looks something like this. X is approaching some point, and it's just one function over another function. Well, if we have that our first function equals the limit as x goes to a of our second function, and they both happen to be 0, or they both happen to equal infinity, well, then we can say that the limit as x goes to that same point a of f of x divided by g of x is equal to the limit as x goes to a of the derivative of f divided by the derivative of g. Now, one thing to note is this is not quotient rule. It is just the derivative at the top over the derivative at the bottom in this case. So let's do a quick example. Let's say we have the limit as x goes to infinity of x squared minus 3 over x cubed plus 1. Well, if we plug in infinity, or take the limit as x goes to infinity, we can see on top we have infinity because x squared goes to infinity, and on bottom we also have infinity. So then we can apply L'Hopital's because our top function and our bottom function both go to infinity. Well, taking the limit of the top, we would get 2x, and on the bottom we would get 3x squared. From here we do have a couple of options. We can either say, well, the top also goes to infinity, the bottom still goes to infinity. We can apply L'Hopital's again, or we can just cancel on top and bottom. And here we can see that this will go to 0. If we applied L'Hopital's again, this would get us 2 divided by 6x, which still goes to 0. Couldn't that problem be solved without L'Hopital's? Yes, it could. It certainly could, but I was just using it as an example for a different method of solving it. There are some problems that it's just like other limit problems or other math problems. There are easier ways to solve this one and harder ways to solve it. In my opinion, L'Hopital's is really easy just because it's a derivative. Derivatives are pretty straightforward to calculate. So that's why a lot of your homeworks earlier in the semester said, solve this limit, do not use L'Hopital's because it made it really easy. Makes sense. All right, we'll go ahead and do a couple of practice problems. Solve the limit. And I will give you guys a few minutes to work on that. The last one is pretty tough, so don't worry if you can't figure it out. I just threw it in there because it'll also double as an example. So go ahead and give it a go. You have time.
Same way,
So the last one, I don't think is correct. The other three are though.
That's one you use like water differentiation, right?
No, not really differentiation. All right, let's go ahead and go through these problems. The last one is not actually impossible. It's just a little more fun. Let's see, we'll start with the first one. The first one, if we plug in infinity, we would get infinity over infinity. So we can, again, apply L'Hopital's. And we get e to the x divided by 3x squared. Again, apply L'Hopital's. And one more time, because we're still getting infinity over infinity. And in this case, we can clearly see that this one will go to infinity. Our second one, if we plug in 0, we would get e to the 0th is 1, minus 1 is 0 on top, and on bottom the sign of 0 is 0, so we have 0 over 0. We can apply L'Hopital's. We take the derivative of the top, and we get 2e to the 2x. And we also take the derivative of the bottom, and we get cosine of x. Well, now when we plug in 0, we would get 2 times e to the 0th, so 2 times 1, all over the cosine of 0, and cosine of 0 is 1. So we would get 2. For our third one, what we want to do is we actually want to rewrite this a little bit. Right now, it's not in the form of f of x over g of x, which is what we want. Luckily, we have an e to the negative x, and we can really easily just write that in the denominator like so. Now we're getting infinity over infinity, but we can apply L'Hopital's, and we take the derivative at the top is 1, derivative at the bottom is e to the x, and this we can see will go to 0. This last one is fun. So what we're going to do is I'm actually going to say that the limit as x goes to infinity of x to the 1 over x is some number L. And now I'm going to take the natural log of both sides. Well, from here, I can apply log rules and write my 1 over x out front of my natural log as a coefficient, which means that now I have a fraction, just like L'Hopital's ones. And when I plug in infinity for x here, I would get infinity over infinity, so I can apply L'Hopital's. The derivative of natural log of x is 1 over x. The derivative of x is just 1. So that would be the limit as x goes to infinity of 1 over x. And this is 0. Now, importantly, what I have here is I have that the natural log of my limit is equal to this 0 here. What I'm looking for is just L by itself. So to cancel out this natural log, I'm going to raise both sides to the power of e. So then I get L is equal to e to the 0th. So L is equal to 1. My limit is 1. Does that make sense?
Yep.
Did you just forget the very last step?
Yeah.
Yeah. I mean, hey, you got most of it, so.
I guess. Fortunately.
Yeah. Does this make sense to everyone? Yeah, it was a bit tricky. It's something you might see crop up occasionally, so it's good to remember this trick. It's kind of similar to log differentiation, like you mentioned, but just good to remember. Well, that is all for this review session. If anyone has any other questions, let me know, but if not, thanks for coming. Of course, you too.